Okay, so we're studying the chapter now on group theory. So a group is something that has a very short and concise definition, but it has a lot of substance hidden in the definition. So a group, G, is a set with a binary operation for example, multiplication. You take two numbers, you multiply them, you get one number. Or addition. Take two numbers and add them, you get another number. That satisfies the following properties. First of all, the operation is associative. And I'll write everything using multiplicative notation. If you take x times y and multiply it by z, that's always the same as multiplying x with yz for all x, y, and z in the group G. So your addition or multiplication has to be associative. If you were writing the operation with a plus sign, this would be x plus y plus z is x plus y plus z. So this is associativity written with multiplication, and this is associativity written with addition. Second, the existence of an identity element. It's called E in the group G, such that E times x equals x, and x times E equals x for all x in the group. Again, if you were going to write this additively, you might write E plus x equals x, and x plus E equals x. So very often when you're using addition as your binary operation, we write the identity as 0. So you would say 0 plus x equals x, and x plus 0 equals x. So sometimes we use the number 0 as the symbol for the identity. Just as in multiplication, sometimes you'd use the number 1. 1 times x equals x, and x times 1 equals x. But whether you use E or 1 or 0 is a choice. Doesn't really matter. It's just notation. And third is existence of inverses. It says for all x in the group, there exists, there exists y in the group such that x times y and y times x equals the identity. So, for example, 3 times 1/3 is 1. And 1/3 times 3 is 1. So the inverse of 3 is 1/3. Or if you're writing things additively, and if the identity is 0, 2 plus minus 2 is 0, and minus 2 plus 2 is 0. So under addition, the inverse of 2 is -2. And those are the three properties of a group. That's it. There's one other property that some groups have, but not all groups. We say that G is commutative. And a synonym is abelian. If x times y is y times x for all x and y in the group. Or if you were writing this additively, x plus y equals y plus x. Again, for all x and y in the group. So that's all a group, that's what a group is. And you've seen many, many, many examples of groups. For example, the integers, z, that's all the integers, 0, plus minus 1, plus minus 2, and so forth, is an additive abelian group. The real numbers are. And the rational numbers are fractions. Q are also additive abelian groups, and the complex numbers. Now, with the integers, you can not only add them, you can multiply them, but under multiplication, they do not form a group. Because, for example, there's no multiplicative inverse of 3 in the integers. If we let, it's called Q star, be the rational numbers with 0 removed. So this is the non-zero fractions, the non-zero rationals. This is a multiplicative group. And it's abelian. And the identity is the number 1. So the inverse of 2/3 is 3/2. Because 2/3 times 3/2 is 1. And also, if I take the non-zero real numbers, this is also a multiplicative group. You have to throw out 0 because 0 doesn't have an inverse. 0 times any number x is never equal to 1 for all x. So 0 has no multiplicative inverse. So if you include 0, you will not have a group. But if you throw out 0, in the rationals, the reals, even the complex numbers, these are all abelian groups under multiplication, the non-zero numbers. There's another very important abelian group we've seen, if we call it Z sub m, or sometimes written Z mod mz. This is the set of congruence classes modulo m. So this is the set of all classes A plus mz, where A is any integer up to m minus 1. So this is, and we can add. We saw this. If you take two congruence classes, A plus mz and B plus mz, you can add them just by adding the numbers A plus B. So for example, if you have m equal to 7, if you take the congruence class 5 plus 7z, and you add it to the congruence class 4 plus 7z, that's 5 plus 4 plus 7z. 5 plus 4 is 9. And 9 is congruent to 2 mod 7, so this is the same as 2 plus 7z. So here we can add congruence classes, and the identity is the congruence class of 0. That's just a set of all multiples of 7. That's the identity. So the set of congruence classes modulo m is an additive abelian group. And the difference between this and these other groups we were looking at is this is a finite set. There are only 7 congruence classes mod 7, but those 7 elements form a group. Any questions about that? Suppose you have two groups, G and H. So suppose we have two groups, G and H, and a function f from G to H. So for example, suppose we take G to be the real numbers under addition. Right? So if you have two numbers x and y, they get sent to x plus y. And suppose H, let me let H be, I'll call it, well, this is the strictly positive real numbers. So the star means we're throwing away zero, and greater than zero means positive. Just the positive real numbers under multiplication. So the real numbers under addition form an abelian group. The positive real numbers under multiplication for another abelian group. And in pre-calculus, you learn a very nice function from G to H, namely that f of x be equal to e to the power x. That's a function that sends every number x to e to the x. I mean, you learn to graph that in calculus. This is the graph of y equals e to the x. For every real number x, you get a positive number e to the x. So this is a function from the group G to the group H. And this function has a very nice property. Under G, if you have two numbers x and y, you can add them. So what is f of x plus y? That's e to the x plus y. But you learn the rules of exponents. This is e to the x times e to the y. And e to the x is f of x, and e to the y is f of y. So this function f from G to H has this very nice property. G is a group under addition, and H is a group under multiplication. If I take x and y and I put them together and then apply f, that's the same as taking f of x and f of y and putting them together in the group H. So a function with this property is very important. It's called a group homomorphism. So if you in general have two groups G and H, is a homomorphism if f of, let's say, xy, I'm just going to write multiplication as the generic operation. F of xy is f of x times f of y for all x and y in G. So a function with this property is called a homomorphism. And an isomorphism is a function with the same property. Homomorphism that's one-to-one and onto, what we call bijection. That means one-to-one and onto. So for example, this function, e to the x, is one-to-one and onto. So if x is different from y, real numbers, then e to the x is different from e to the y, because this function is monotonically increasing. If I take a number x and a number y, this is e to the x, this is e to the y. If y is bigger than x, e to the y is bigger than e to the x. So f is 1 to 1. And if I take any number, let's call it z. So for all real numbers z positive, log of z, natural log of z, is some real number. And f of log z, that's e to the log z, but e to the log of a number is just the number. So for any positive number z, if I take its natural logarithm, f of log z is z. So f is onto. So this function, e to the x, from the real numbers as an additive group to the positive numbers as a multiplicative group, is an isomorphism. And even though the real numbers under addition and the positive real numbers under multiplication look like different groups, from the point of view of group theory, they are isomorphic. That's another word for saying that as groups, they are the same. They're essentially the same. And this notion of isomorphism is very important. In fact, in the text, it is on page 88, definition. So page 88, definition 2.1.13. So let me prove a few statements to show how strong this property of being isomorphic is. So in terms of notation, so G with this symbol means group G is isomorphic to group H. Right, so that is this very important notation. So here's a little fact, if you like, or not theorem, but if G is isomorphic to H and G is abelian, then H is abelian. Proof. Suppose I take a function, I'll call it phi, because is the notation the book seems to like. The phi from G to H be an isomorphism. That means G of xy equals G of x times G of y for all x and y in G, and phi. And phi is a bijection. It's 1 to 1 and onto. So suppose we let H1 and H2 be an H. I know that G is abelian. I want to show H is abelian. So I must prove that H1, H2 equals H2, H1. That is, the multiplication in H is abelian. How can I prove that? So phi is onto means there exist elements G1 and G2 in G such that phi of G1 equals H1 and phi of G2 equals H2. So let me be a little bit clever. This is what I want to prove. So how can I prove H1, H2 equals H2, H1? Well, H1, H2, that's phi of G1 times phi of G2. But this phi is an isomorphism. So phi of G1 times phi of G2 is phi of G1 times G2. But G is abelian. G1, G2 is the same as G2, G1. So phi of G1, G2 is phi of G2, G1 because G is abelian. And again, because phi is an isomorphism, this is phi of G2 times phi of G1. And phi of G2 is H2 and phi of G1 is H1. So I've proved that H1, H2 equals H2, H1. Just using the fact that H is isomorphic to an abelian group. Any questions about this? I already proved the first results about groups. That G be a group. So we know every group has an identity element. Suppose we have two elements and let E and E prime be identity elements. I claim the identity is unique, that E has to equal E prime. So how can I prove that? So if I look at E times E prime, because E prime is an identity, E times E prime is equal to E. Because E prime is the identity. But because E is also an identity, E times E prime is E prime. E is an identity. So we have E equals E prime. A group has a unique identity. Suppose X is in the group, and suppose it has two elements. XY equal YX equals the identity, and XZ equals ZX equals the identity. I want to show Y equals Z. Then I want to show that there's a unique inverse to every element in a group. So the proof is very simple and pretty. Suppose I take Y. Y is, of course, equal to Y times the identity. But the identity can be written as X times Z, because Z is an inverse of X. And because group multiplication is associative, this is the same as yx times z. But yx is the identity, and E times Z is Z. So if it looks like if two different elements in the group act as the inverse, they have to be equal. So every element in a group also has a unique inverse. And how do inverse operations work under multiplication? So for all x and y in the group, if I take xy and I multiply it by y inverse x inverse, I claim I claim, this is what I want to prove, that the inverse of xy, and I can write this symbol for the inverse of an element because I just proved the inverse is unique. The inverse of the product of two elements is the product of their inverses in reversed order. So that's the statement. Why is that? Well, by associativity, this is x times y inverse x inverse. X, y times this is x times this times this. And if I apply my associativity again, this is x times y inverse times x inverse. And y times y inverse is just the identity. And the identity times anything is just the anything. And x times x inverse is the identity. That proves if you take xy and you multiply it on the right by y inverse x inverse, you get the identity. And exactly the same argument would hold if you took y inverse x inverse and multiplied it by xy. This would be y inverse times x inverse times xy, which is y inverse times x inverse x times y, which is y inverse times ey, the identity, which is y inverse y, which is the identity. So if I take xy and I multiply on the right by this, or I take xy and I multiply on the left by the same thing, in both cases, I get the identity. So that's the proof of this assertion. And let's make one other observation. If I have a group G with an element X, it has an inverse. But every element has an inverse, so X inverse has an inverse. And I claim that the inverse of X is X. And the proof is, if I take X inverse times X, I get the identity. And if I take X times X inverse, I get the identity. So what do I multiply X inverse by to get the identity? X. So the inverse of X inverse is X. So that is the beautifully simple proof. It's a very short thing to write down, but it only makes sense if you have the words. So I'm saying the words, but if you had to prove this, well, as an exam question, you would have to explain why this is true. It's what justifies this implication. We also have the notion of cancellation. If you have ax and y in the group, and ax equals ay, then x equals y. That is, you can cancel the a. Proof. If ax equals ay, then a inverse times ax equals a inverse times ay. But this is a inverse a times y, that's y. And this is a inverse a, the identity times x, which is x. So x equal y. So you can cancel. It is not true always that if ax equals ya, that implies x equal y. So this might happen in some cases, for example, if the group is abelian, but in general, that's not true. You can only cancel an element if it's on both sides, the same side. It's on the left or the right on both sides of the equation. So left multiplication of x by a equals left multiplication of y by a. You can cancel the a's and get x equals y. But not this. So what is called the order of a finite group, G, which is denoted by G with absolute value signs around it, is the number of elements in G. So for example, if you take Z7, the integers mod 7, the order of that group is 7. See, what's another example of a group? Suppose we look at the permutations of the numbers 1, 2, 3. This is what is called, this is a group. This is the symmetric group S3. And you remember you can write every permutation sigma in S3. So you can write as it's a function from the 1, 2, 3 to itself. That's 1 to 1 and on to. So this goes to something A, B, C. And the number of permutations of 3 objects is 3 factorial, 1 times 2 times 3, which is 6. So the symmetric group S3 is a group of order 6. It's also called the permutation group. And this group is non-abelian. So for example, suppose we take X to be the transposition 1, 2, and Y to be the transposition 1, 3. So what is so this is the permutation that sends 1 to 2, 2 to 1, and 3 to 3. This is the permutation that sends 1 to 3, 2 to 2, and 3 to 1. And what is X times Y? So this is composition of functions. 1 goes to 3, goes to 3. 2 goes to 2, goes to 1. 3 goes to 1, goes to 2. So XY is the permutation that sends 1 to 3, 2 to 1, and 3 to 2. If you were to write this as a cycle, it's the cycle 1 goes to 3, goes to 2, goes back to 1. But what is YX? So this is the multiplication in the opposite order, or composition of functions in the opposite order. So 1 goes to 2, goes to 3. 2 goes to 1. Sorry, 1, 2 goes, sorry, 1 goes to 2, goes to 2. 2 goes to 1, goes to 3. 3 goes to 3, goes to 1. So this is the permutation that sends 1 to 2, 2 to 3, and 3 to 1. And these are different. So S3 is not abelian. Finite groups are very interesting. They're finite, so in some sense they're simpler than infinite groups. So permutation groups are always finite. If we look at the group Zn, which is the additive abelian group of congruence classes modulo n, excuse me 1 second. Yeah. So Zn is the additive abelian group of congruence classes mod n. So this is a finite group of order n for every n. So there's a group with 1 element, 2 elements, 3 elements, and so forth. These groups Cn. The permutation group or symmetric group Sn has order n factorial. And under multiplication, composition of permutations is not abelian, so long as n is at least 3. Because every one of these groups contains the 2 cycles, 1, 2, and 1, 3. And we just saw that if you multiply them in opposite orders, you get different permutations. So every symmetric group or permutation group is not abelian, non-abelian, so long as n is at least 3. As long as you have 3 numbers, you can pick 1, 2, and 3. So for n at least 3, no symmetric group can be isomorphic to the additive group of congruence classes, mod n factorial, because if one were abelian, the other would have to be abelian. Let's look at another group. Let's look at the symmetries of a rectangle. So here we have a rectangle. And I'll label the vertices. And what are the different operations you can do to a rectangle where you lift it up and turn it around? You don't cut it up into pieces, and you put it back into the same space. So one thing you can do is pick up the rectangle and put it back exactly where it was. I'll call that E, like that's sort of like the identity symmetry. You don't do anything. Another thing you can do is pick up the rectangle and flip it around this line through the vertical line through the center. So 2, 3 ends up here, and 1, 4 ends up there. Let me call that operation A, say. So A is the symmetry where you rotate the rectangle around the vertical line. Alternatively, I could take the rectangle, draw a horizontal line through the center, and rotate it like that. And then the 1, 2 on the bottom end up on top, and the 4, 3 on top end up on the bottom. So let me call that operation B. And there's one more symmetry of this rectangle. I think, let's see. I could flip it vertically and then flip it horizontally, and I get 2, 1, 3, 4. And let me call that operation C. That is, I can pick up this rectangle, flip it horizontally and vertically, or vertically and horizontally, it would be the same thing, and end up with this. And you notice when I put the rectangle down, vertex number 1 can be at any one of the 4 corners. But once I set down vertex 1, I have no choice about where the other vertices go or where the rest of the rectangle goes, because 4 is the short side connected to 1. So it has to be either 1, 4 or 4, 1 everywhere. So there are exactly these 4 symmetries of the rectangle. So let's say let G be the symmetries of the rectangle. So this is a group, and it has exactly 4 elements. The identity A, B, and C. Because I can perform any one of these operations and then do it again and then do it again. And that's what it is. Let's work out the multiplication table for this group. So this is this group of symmetries of the rectangle. And it's the binary operation is just do one symmetry and then do the next. So if E times E, that means do nothing followed by do nothing, then that does nothing, that's E. What is E times A? That means do A and then leave it fixed, so that's the same as A. I mean, E is the identity in this group. EB means do the symmetry B and then E, so that's B. Or do the symmetry C and then E, so that's C. And similarly, A times E means take your rectangle, leave it fixed, and then perform A, so that's the result is A. Leave it fixed and then perform B, the result is B. Leave it fixed and then perform C, that's C. So that first row and first column, they're easy to fill in for the multiplication table. But what about the rest? That's more interesting. A times A, that's what goes here. That means do A and then do A again. So A flips the rectangle around a vertical axis. You get this. If you flip it again, you're back where you started. So A times A is the identity. In fact, when you apply any one of these operations twice, you get back the identity. If you take your rectangle and you flip it horizontally, you get this. If you flip it horizontally again, you're back where you started. And here, if you take A and you move A to the diagonally opposite vertex, and then you do it again, so A goes to the diagonally opposite vertex, that means it's back where I started. That's the identity also. So this main diagonal of this multiplication table is all the identity. What about A times B? This says A times B means perform the symmetry B and then perform A. So B, that's a horizontal rotation that sends 1 up here, and A is the vertical rotation that sends 1 over here. So the only symmetry that sends 1 to this upper right-hand corner is C. So AB equals C. What is AC? C sends 1 to the diagonally opposite corner, and A sends 1, it flips it up. So, or down. So so I want to calculate A times C. So C sends the rectangle here. A is the operation which flips vertically, so 1 ends up over here. You get 1, 4, 2, 3. That's equal to B. What is B times A? You flip A vertically, B horizontally, you end up with C. So I want to stop for a minute and give you a chance to fill in the last three blocks of this table. This is per BC, this is CA, this is CB. So this is the permutation where you first apply the symmetry C to the rectangle and then a symmetry B. This is A followed by C, this is B followed by C. So I want to give you a chance to calculate these things and tell me what you get. So then we pause so you have a chance to do that. So someone wrote that C times A is B. Let's see. If you apply A, that means that's this vertical rotation. And then you move one to the diagonally opposite position, which is over here. That is B. So you are correct. This is B. And BC is correctly identified as A. And CB is correctly identified as A also. So this is the multiplication table for the group of symmetries of the rectangle. So the group has four elements, A, B, C, and E, and you'll notice every row is a permutation of A, B, C, and E, and every column is a permutation of A, B, C, and E. And that's always the case with the multiplication table for a group, for a finite group, certainly. Yeah. Each row and column is a permutation of the elements. Every element occurs exactly once. And there's an interesting way to prove that, which I will leave for you to think about. So we have two abelian groups so far of order 4. We have G, which is the symmetries of the rectangle, and I just computed its multiplication table. We also have Z4, which is congruence classes modulo 4. So this is the group 0 plus 4Z, 1 plus 4Z, 2 plus 4Z, and 3 plus 4Z. Now, for the group G of symmetries of the rectangle, we saw that E times E is E, A times A is E, B times B is E, C times C is E. So this group has the property that X squared is the identity for every element X in this group G. X times X, X times X is the identity. But in the group of congruence classes, the equivalent statement isn't true. It is not true that X plus X equals 0. It means the congruence class of X plus the congruence class of X equal congruence class of 0. But this is not true for all X in the group. For example, 1 plus 4Z plus 1 plus 4Z is 2 plus 4Z, which is not 0 plus 4Z. These are the numbers that leave a remainder of 2 when you divide by 4. These are the numbers that are exactly divisible by 4. So I claim that's enough to show that these two groups are not isomorphic. So I claim this group, an additive abelian group of 4 elements, is not isomorphic to Z4. And what is the proof of that? So that phi from G to Z4 suppose there exists an isomorphism from G to Z4, phi from G to Z4. So for every x that is a symmetry of the rectangle, x squared is the identity. So for example, so phi from G to Z4 is a bijection. It's 1 to 1 and on to. So we can say that there exists an x in G such that, so this is some symmetry of the rectangle, and phi of x is the congruence class 1 plus 4z. So what does that imply? So because phi is an isomorphism, phi of x squared, which means phi of x times x, is going to be phi of x plus phi of x. But x squared is the identity. You square any element in G, you get the identity. This is phi of the identity. And the identity always maps to the identity. I'll show that in a second. Phi of the identity has to be 0 plus 4z. But phi of x is 1 plus 4z. So this is 1 plus 4z plus 1 plus 4z. And that's 2 plus 4z. And 2 is not 0. So I have a contradiction, right? If there existed an isomorphism between the group of symmetries of the rectangle and the additive abelian group of congruence classes mod 4, then if I take any congruence class, 1 plus 4z, there's some element x that gets mapped by phi to 1 plus 4z. There's some element x in the group such that phi of x is 1 plus 4z. But phi is an isomorphism. So phi of x times x is phi of x plus phi of x, right? Because phi is an isomorphism. But phi of x is 1 plus 4z, and if you have 1 plus 4z to itself, you get 2 plus 4z, which is not the congruence class of 0. But x times x is x squared. And x squared is the identity, and the identity always gets mapped to the identity, I claim. So that's a proof that the 4-element group G is not isomorphic to the 4-element group Z4. You can have finite abelian groups of the same order that are not isomorphic to one another. So let me prove the fact that I just used, which says the following. So an isomorphism is a function that is a bijection and satisfies a certain group theoretic property. So let's say a map phi from a group G to a group H is a homomorphism if phi of xy is phi of x times phi of y for all x and y in the group. Let E, let me say E sub G be the identity element, be the identity in G, and E sub H the identity in H. I claim that if you take the identity in G and you apply the function phi to it, that always gives you the identity in H. Proof. Let's see. How can we prove this? So E sub H, sorry, put it like this. Phi of E sub G, of course, the identity multiplied by itself is still the identity. Let me try and make this more legible. So we know that the identity is always the identity multiplied by itself. 1 times 1 is 1. So phi of EG is phi of EG times EG. And because phi is this homomorphism, it has this property, this is phi of EG times phi of EG, where phi of E sub G is some element in H. So it has an inverse. So there exists phi of EG inverse in H. So if you multiply phi of EG times phi of EG inverse, that's phi of EG times phi of EG times phi of EG inverse. Multiplying an element by itself, by its inverse, gives you the identity in H. This is E sub H. And this is the same as by associativity, phi of EG times phi of EG times phi of EG inverse. That's phi of EG times the identity in H, and multiplying anything by the identity, this gives you what you started with. So if you look at this equation, phi applied to the identity in G is the identity in H. That was the group theoretic statement I wanted to prove. So this is the solution of one of the homework problems, 2.1.5, which is to show that the groups Z4, that the group Z4 and the group of rotational symmetries of a rectangle are not isomorphic. They are both abelian groups with 4 elements, but they are not isomorphic to each other. Okay. Now, suppose we have the multiplicative group R star, which is the non-zero real numbers. And contained in that is the group Q star, which is the non-zero rational numbers. And contained in that is, for example, Q star greater than 0, the strictly positive rational numbers. So these are all, in fact, multiplicative groups. There are 3 of them. This is contained in this, and this is contained in this. So if you have a group contained in a bigger group, then the smaller group is called a subgroup of the bigger group. So H is a subgroup of a group G if H is also, it's a subset, and H is also a group. So this is a subgroup of this, and this is a subgroup of this. Another example. Suppose I take G to be the integers under addition and H to be the even integers. That is 0, plus or minus 2, plus or minus 4, and so forth. I would write this often as 2z, just all multiples of 2. So if I take 2 even numbers, say 2m plus or minus 2n, that's 2 times m plus or minus n. The sum or difference of 2 even integers is an even integer. And 0 is even, 0 is 2 times 0. So this set is a group under addition. It's a set of even numbers, and it's contained in the set of all numbers. In fact, for all n greater than or equal to 1, nz, which is the set of all multiples of n, 2n, 3n, 4n, and so forth, and negatives, plus or minus n, plus or minus 2n, and so forth. This is closed under addition and subtraction. This is a subgroup, and z is a subgroup of z for all n. If I take n equal to 0, 0 times z is just the number 0. But this is a subgroup. This because 0 is a group. 0 plus 0 is 0. 0 minus 0 is 0. And 1 times z is just z. In fact, every group has 2 that are trivial subgroups. G is a subgroup of itself because G is contained in G. And if you take just the identity element E, this is also a subgroup of G. Right? Because E times E is E, and E inverse is E. So the set consisting of just the number 0 is an additive abelian group. It's trivial. Or under multiplication, the set consisting just of the number 1 is an additive abelian group. So that's the notion of a subgroup. And there's one very important class of subgroups, which are called cyclic groups. Let G be a group and let A be an element of G. Suppose let H be the set consisting of E, A squared, A cubed, A to the fourth, all the powers of A, but also A inverse squared, A inverse cubed, and all the powers of A inverse. And just as notation, we usually write A inverse to the K as A to the minus K. So that's just notation. A to the minus K means the kth power of A inverse. So it's also true that this is the same as the inverse of A to the K. And I claim H is a subgroup of G. And the reason is simply that, for example, if K and L are non-negative integers, then A to the K plus L, this is just A to the K times A to the L, the rules of exponents. You multiply A by itself K times and then another L times. That's the same as multiplying A by itself K plus L times. And if K and L are both negative, then, or let's say K and L are positive, and A to the minus K times A to the minus L, this means A inverse to the K, A inverse to the L. That's A inverse to the K plus L. That's A to the minus K plus L, which is A to the minus K minus L. It's exactly, or let me write this, this is A to the minus K plus minus L. And if you have A to the minus K times A to the L, suppose K is less than or equal to L. This is A to the minus K. This is A to the K plus L minus K. Because K plus L minus K is L. This is A to the minus K, A to the K, A to the L minus K. This is A inverse raised to the kth power times A to the kth power. These cancel. That's A to the 0, which is E. This is A to the L minus K. So for all powers of A to the K plus L equals A to the K times A to the L for all integers K and L. So this subgroup H, which I will write it as A with these brackets around it. So this means the set of all A to the K for K and Z is a subgroup. It's called the cyclic subgroup of G generated by A. So this is really very important in group theory. These cyclic groups are they're sort of the simplest groups you can find in many cases. They're really very fundamental. What are some more examples of subgroups? So we have the group S, let's say S4. which is the symmetries or the permutations of 1, 2, 3, 4. Suppose I take H to be the set of all permutations of 1, 2, 3, 4 that keep the number 4 fixed, sigma 4 equals 4. So it's all permutations 1, 2, 3, 4, where 4 goes to 4, and here you have some permutation of 1, 2, and 3. I claim H is a subgroup. That's 4. So if sigma and tau are in H, that means sigma of 4 equals 4, and tau of 4 equals 4. So if I take sigma tau of 4, that's sigma of tau of 4. Tau of 4 is 4, so that's sigma of 4. Sigma of 4 is 4. So sigma tau is also in H. And if sigma of 4 is 4, that means sigma inverse of 4 is 4. So sigma inverse is in H. So H is a set of permutations. It's not empty. The identity applied to 4 is 4. So H contains the identity, is closed under multiplication and inverses. This is a subgroup. So this is a very nice example of a subgroup of a group. Suppose in S4, I take the permutation sigma equal to just 1, 2. What is the cyclic subgroup generated by sigma? So I have the identity, I have sigma, but what is sigma squared? If sigma is 1, 2, sigma squared is the identity, and sigma inverse is the same as sigma. So this 2-element set is a subgroup. It's closed under multiplication and contains the inverse of each of its elements. So every transposition generates a 2-element cyclic subgroup of the group. Okay. So what we've been talking about today are sections 2.1 and 2.2 in the text. And these are really very important. So I'll continue to talk about this on Monday. I owe you a lecture. I had a medical appointment on Monday, and I said I would record a lecture and upload it to YouTube, which I will. But in fact, we have almost a 2-week vacation, 2-week break. So we have a lecture on Monday, and then Wednesday, the following Monday and Wednesday is spring break at Lehman. So after Monday, the next lecture on Zoom live is 2 weeks later. So I will, during that period, upload the missing lecture so we haven't lost anything. And if you have questions, even during the break, you are encouraged just to email me and I can set up a Zoom time when we can talk about anything in algebra you want to ask about. Okay. Any questions about any of this? This is really fundamental, the most fundamental part of this course, learning properties, the basic theory of groups. And we're going to look at more and more examples of groups. We're going to study isomorphisms and homomorphisms in more detail. And we're going to learn something very important, which is called the quotient group of a group, and something called Lagrange's theorem for a group. And really, we're going to spend the rest of the semester on chapter 2, and as much of it as we can cover, certainly there are, I would like to do all of chapter 2. So we have slightly less than half of the semester left. So that should be ample time. But it is a lot to learn, and I really encourage you to study the book very carefully and very often. Okay. Any questions before we leave for the day? There is a Zoom problem session today at 1 o'clock. So if you have questions about algebra that come up in the next 2.5 hours, I encourage you at 1 o'clock to log in. If not, it's kind of chilly outside, but it's a nice looking day. So everyone be well, and see you next Monday. All right. Bye all.